Hello, everyone. My name is Ian, and this is Reading Types Like a Parser. So you may know me as Lectron Pusher on the Discord. I recently refactored parts of Types Parser, and I'm currently working on moving math parsing into runtime mode. Types has a lot of features that make it easy to type documents, but the question is, how do we go from knowing that structure, turning this unstructured text into something that we can highlight with syntax and that can create and produce our documents? And here I have an example of a Lectron pusher, literally. So the way that we understand language syntax is by parsing. Types has a lot of interesting syntax that we need to make use of, and this talk is going to be covering some of the interesting techniques that we make use of that I learned about going through the parser refactor. We had a lot of there were a lot of things that I had learned about when doing this, and I wasn't sure. And much of what we're doing here is not new. We're building up from technology that's existed for a long time, but I just want to summarize and explain it because I think it's great. So types has a lot of interesting syntax. We have modes that change the meaning of characters. We have lists in markup that do not follow the normal definition of context-free. And math has these weird operators like hat, prime, and underscore that chain in a way that we don't see in other languages. And in code mode, parentheses are ambiguous. So we're able to understand these features with a few different parsing techniques. First is lexer modes, newline modes, Pratt parsing, and how we're using stop sets, and then finally memoization. So parsing, just in general, to give an overview, is giving meaning to data. We start with source code as a string of bytes. We've got our main.type file here that's just byte, 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 etc. And it just keeps going. How do we get information from this into the language? That's all we have to start with. We view information in layers of abstraction. We start from the byte level, and then we get characters. And then on top of characters, we understand them by using a lexer to understand a lexical token. A lexicon is just a thing that describes words. It's a way to describe your dictionary, what possible words. And in programming languages, we use this to mean where do tokens end and start and stop? Where do we understand individual parts? Then finally, we build up from that syntax trees. We create a concrete or an abstract syntax tree, depending on what we need at the moment. Right now, the parser iterates over characters just from Rust. We get a lot of usage out of Rust's character abstraction for parsing strings. And then the lexer is the view over those tokens in our parser. So here's an example of some source code that we might view at different layers. On the left, we have hello, highlight, Berlin. So on the left, we have just characters. We can view this as an array of characters that we're going to iterate over one by one by one. HELLO. And then we're interpreting the bytes that make up all of this different text into those characters. That's a step that happens at the very low level. Once we get into that, we're going to be using lexical tokens, and here we're making use of lexer modes. The parser drives the lexer by knowing which mode it's in. In different modes, it uses tokens to make different things. At the beginning, the first word hello is just text. We're going to interpret that in markup mode. We interpret a space and we interpret a hash, and then at the hashtag, we recognize, okay, this is going to start moving us. The parser recognizes that we need to switch to code mode. The parser tells the lexer, change your mode. And now the next word, highlight, changes to being parsed in a different mode. Instead of being parsed as a word of text, it's parsed as an identifier for markup to recognize as a function call. We produce a bracket, and then we switch back into markup mode. We go into text, we get the word Berlin, then we go back to our bracket and we exit code mode, exit, we do a little bit of stepping from code mode back to markup mode, and then we get the exclamation point at the end. We're understanding the lexical tokens at a very low level, but driving it by modes. This is how Typst is able to highlight different things. Then the other two are concrete syntax and abstract syntax. Concrete syntax includes all of the text of the source file. It includes our basic comments, our white space, everything that you're going to need to do things like an IDE. to highlight comments special, to draw, to allow you to jump to different locations. It includes every piece of information that we know about the text. But we don't need all of that information to implement types. There are a lot of things like white space indentation or comments that don't affect the rest of parsing. So instead, the final output of the parser is the abstract syntax tree. This abstracts over all of that unnecessary detail and converts it to just a view of, we have a string of markup that's going to have text and a space, but we're going to ignore the hashtag. You don't care about that. We're just going to have a function call. Function call does have the identifier, but now we're going to give extra information. We're going to give a view over the arguments as being either positional or named, something like that. And then we can have more structured information by interpreting the concrete syntax tree. At the end, we then add the exclamation point to produce our text. So in this way, we're able to view the same source at different layers and build information. It's not that at the character level, we could have done everything by just going through all of the bytes, every single bit at a time. But that's horrible. That's going to be incredibly slow. Instead, we found that, or instead, like the community of programming languages has found that over time, we get better information by viewing different layers one by one. So one of the things that I did with the parser refactor was expand our use of newline modes. We were already using newline modes to separate code mode by saying, okay, if we create a new line, the parser is going to act like we're at the end of a section until we exit out of that new line mode. And that allows us to break statements in code very easily. But in markup mode, we have some interesting features. Lists in markup are not a context-free grammar. In most parsing for programming languages, there is a massive amount of focus on context-free parsing. But the problem is that context-free is not actually common. Context-free means that individual tokens don't change their meaning anywhere. And it's a very good way to parse a list of a one-dimensional list of characters. But in markup, we actually have a two-dimensional structure to our source text. So in creating a list, we have the column that the list starts on that is independent of each line. There's no way to figure out the column very well using a context-free grammar. So we need to use get that information into the parser somehow. The idea here is that we create the idea here was initially, my idea was to move newline modes when we initially had them into the lexer, simplifying that structure and giving us less information at the next level, but making it so that we don't need to handle that information. But I got this wrong at the beginning. I realized that it was harder to understand the source text after putting the newline modes into the lexer modes, pushing them all into one. And separating them, I made it so that the lexer understood just the lexer modes, and the parser had a view over the newline mode, where the newline mode is going to contain information about the indentation of each section. And then the parser can interpret, okay, my newline mode is at a certain level of indentation, it's at a certain column. So if I'm at a list, I will break that into a new nested list if it's spanned further, or I'll break it lower otherwise. And one of the problems is that the comments can end anywhere. There can be white space at any different section. So we have to have context sensitivity to know where we're going to parse text. So one of the updates is that now lists are able to parse based on just the full exact column than before. So now we're going to get into math mode and math expressions. To parse math expressions, we use a really interesting technique called Pratt parsing. Here we have an algorithm for parsing math expressions, and we want to parse the text A/B_C. The question is, which of those, how do we know that we want to have the B_C nested underneath the fraction, underneath the slash? We need precedence of operators to do so. So the Pratt parsing function is really the Pratt parsing function. uh, algorithm is really ingenious. The idea is that we have two parts. We have a loop where we just loop over each thing. But before the loop, we get one node because we know if we call the function, we need at least one node. Then we say we enter the loop and we try to get operators. If we don't have an operator, we're going to be returning. And if we do have an operator, we're going to check. Is its left precedence greater than not above the minimum? We've given in the function a minimum precedence for the operators that it must be above. But if it's below this, then we'll just return the node. The idea is that this operator will then be accessed by the previous iteration of the loop, because below this, we have recursive call. We call parse expression again. We call it parse expert with the operator's right precedence. So if we're here, if we're in the Pratt algorithm, we know that we have some parent. We have some parent operator. And if our precedence is not at the minimum required level, then we break out. We give ourselves the operator that we're going to be parsing to the parent call. And we say their node is going to be using, we're going to take advantage of their left-hand side node. There are a number of blog posts in the community that explain Pratt parsing. I like the one by Matt Clad recently, and there's a very old one by Bob Nystrom, but that go into more detail. But there's an interesting thing that Typst does with operators is that it has to handle operator chaining. The underscore and the hat and primes chain with each other. We can't just give one to the other. We can't just say A underscore B hat C and create parentheses around one or the two. The expression is one full expression. So when we want to parse this system, we make a change to the algorithm. We include information about a stop set. Instead of just checking precedence, we check, am I at this operator that's going to cause me to return? And then we update the algorithm. We say parse expression of the operator's right precedence and the operator's chaining set. So if we were at a prime, we would chain with underscore or hat. If we were at a hat, we would chain with underscore. And if we were at an underscore, we would chain with hat if we're not chaining with anything previously. This gives the algorithm enough information at each step to know that we need new operators. We need to get something else, or we need to stop here and then restart. This introduction of stop sets is really interesting because I haven't seen this anywhere else in looking around at Pratt parsers, and I've looked at a lot of them. So that's an interesting way that we're able to manage parsing underscores and hat in the math expression language. Finally, in code mode, we have to handle ambiguity. This is the most interesting part of how Typst reads expressions. Normally, parsing happens left to right, just from each character going forward. But if we have a following Typst expression where we have an array with X, Y, Z, this might be an array. This might be just structuring of array with 3 elements X, Y, Z following. But if it follows with an arrow, then this is actually an argument list. So we don't know what we're parsing until we've seen the next character. We could solve our problem with backtracking. If we see the end of a parenthesis and then we see an arrow, we just go back. We remember where the start of the parenthesis was, and then we go back and restart our parsing. But there's an exponential problem with the following. If we have parenthesis X colon, this looks like a dictionary. All right, then we're going to get the inner dictionary, parenthesis X colon, looks like a dictionary. We're going to keep trying as a dictionary. Then we get parenthesis X, close parenthesis, we get the arrow into Y, and we recognize that this must be a function. Naive backtracking is just going to exit out to the closest innermost parenthesis. And then it'll reparse parenthesis X as an argument list, arrow Y. And then we'll reach the next closed parenthesis, arrow Y. And now we need to jump out into the second set of opening parentheses. But the problem is that when we reach again the inner, inside, we are not able to reparse. We haven't remembered anything about this inner X. So the inside parenthesis, we still try to parse as a dictionary and array, and then we have to redo the step of, oh, it's actually an argument list when we reach the arrow. So this has an exponential growth, meaning that there are some cases that will effectively take forever to parse. And that's really horrible. We don't want to do that. The answer to this problem is to memoize. Memoization is remembering things, keeping an array of previously seen nodes. The parser adds an array of memoized state that allows it to backtrack and to, at each point, see, have I seen this parenthesis expression before? If so, what does it look like? This requires more storage, but it solves the time trade-off that we would otherwise lose to. So parsing with memoization allows us to handle this ambiguity. And we were actually able to resolve, and during the parser refactor, I resolved a bug that happened with this, where we were incorrectly changing the order of changing the index that we were searching from in memoization because it wasn't fully clear how the code was structured. So this was a bit rushed because I had less time to prepare this than I would like. But thank you guys for letting me come and letting me present. And I'm now open for questions.
First of all, thank you for the talk. And then, of course, if you have any questions, please come up to the front to the microphone so Ian can actually hear you.
I was wondering, in the case where for the hat and the underscore, why can't that be parsed as a tree and then just handle that in the next stage, just correct it somehow in the next stage?
There is an option to handle it as to parse it as a tree and then handle it in the next stage. But we want to keep this as a flat expression because the difficulty arises when we have further nesting of the trees. What if we have parenthesis around, we have A underscore B hat C, but with parentheses around the B hat C? We need another structure to create that parenthesization to separate that. Otherwise, our tree is just going to undo that explicit parenthesization without us recognizing that. So we need to this allows us to handle explicit parenthesization just like any other normal system. But if we don't have explicit parentheses, then we recognize that the next character is in our stop set. It's in the operator's chain. If we were inside parentheses, those parentheses would hide that hat from ever being seen by the stop set.
Thank you. Any other questions? Ian, then if there aren't any other questions.
Hi, Ian. You want to explain a bit what did you work on in the refactor actually? So what was already there from what you showed us? Did you introduce new concepts into the parser?
I didn't introduce too many new concepts. I did change how we use newline modes so that we started to use them in Markup. Before, we didn't have newline modes for Markup. We just used them in code mode to recognize ends. But I changed it so that we would include newline modes, this as a general concept throughout the parser, where in Markup, if we recognize that our indentation is not high enough to be a part of the same element, then we introduce a stop that will cause us to exit out to the next element, and then we'll keep checking if our indentation is at the right level. So this was the main thing that I added. A lot of the parser refactor was really just cleaning up some code and making things a bit more consistent. One of the things that we didn't do before was combine trivia. So trivia tokens are comments and spaces. We would sometimes split trivia in markup mode into different elements. So like the start of this list, starting with D over here, might include that leading comment, but the start of the list with B might not. So that would be inconsistent and make it a bit harder for other tools to recognize the parser, like the TinyMist IDE has to manage code. So having a more regular output helps it there. I did not introduce most of these concepts. The parsing math expressions like von Pratt with stop sets was added a few months before I got here when someone changed the parsing for hats and underscores. And the system of lexer modes was already here for a while too. But I just want to highlight that these are some cool things. I did not come up with a lot of these techniques, and you can find them in other programming languages too.
Thanks for giving us so much insight on the working of the parsers. Great job.
Well, thank you. And thank you again for doing this talk remotely. We really enjoyed it. And we are sending a lot of love from Berlin to you in the US.
All right. Thank you, guys.
Thank you.
Bye.